So what is computer architecture? And, very importantly, why should you care about it? Let's take a look at a press release from October 2011. So if you see what this press release says, it says ARM unveils its most energy-efficient application processor ever, redefines power and performance with the big. LITTLE processing. So big. LITTLE processing. Not exactly sure what that is, but ARM introduced it. So is this important? Is this interesting? Let's look at what some of the press said about this. Deep inside ARM's new Intel killer. So here's an article online which is talking about this new technology that ARM's releasing and saying this is going to kill Intel. Now Intel's a pretty big company, so if they're coming up with something that's that exciting, this must be a big deal. So before we go into what it is, who knows what ARM is? Do you know what ARM is? Have you heard of ARM? Have you ever bought a computer that says ARM inside? Or have you ever gone to a store and seen ARM inside? Or seen an advertisement on television? So I have another question. How many of you own an ARM computer? So if you haven't seen an advertisement that says ARM inside, and you haven't bought one in a store, it's not very likely. But the interesting truth is everyone owns an ARM computer. ARM processors are the things that are inside of cell phones and tablets and printers and all over the place. ARM is a very popular type of processor, but you never really see it. It's known as an embedded processor. Let's take a look at just how big it is. Here's a plot of processor shipments, and these are desktop and laptop PCs in blue versus smartphones and tablets in yellow. And you can see how they've changed over the years. What you see is the desktops have done pretty well, and that the mobile devices, the smartphones and tablets, have started to increase dramatically. And this is ARM. So all of these processors here are basically ARM processors. Now that's pretty impressive. They're growing pretty fast. Now if you look at projections for the next several years here, what you see is desktop continues to grow reasonably fast, but what happens impressively is that the mobile devices take off. And so in 2013, what we start to see is that there are almost twice as many ARM processors being sold as there are processors for desktop and laptop PCs. So these embedded ARM computers are the most common in the world, and it's not surprising that all of you therefore own one. So when ARM introduces something that's really significant, it's not that far off to label it as a possible Intel killer. So let's take a look at what this big. LITTLE thing is. Basically consists of two parts. It's big processor cores for high performance and little processor cores for low power. So we've got two parts here, high performance and low power. If we look at the picture that ARM draws here, you can see they've got their cores on here. Here are the big cores for the high performance, and here are the little cores for the low power. And so that's basically it, big and little cores for high performance and low power. So another question is, why are they doing this? Well, to understand that, we want to look at power efficiency. So this graph here plots power on one axis along here versus performance on this axis. And we can see the range of the big and little processor cores. So the big processor core starts from low performance, or medium performance over here, and goes all the way up to very high performance. But when you get to that high performance, you also have very high power. So the big processor cores are fast, but they use a lot of power. The little processor cores are the opposite. They start down here at relatively low performance and go all the way down to even lower performance. But when you get down to that low performance, you save a lot of power. They're very low power. So why is ARM doing this? Because they want to save your battery, so your cell phone lasts longer. By having high power fast processors and low power slow processors, they can choose the right processor for the right thing on your phone and therefore optimize the power efficiency and save your battery power. So let's take a look at some of the details. Here are two pictures that ARM has released about their little and big processor designs, and you can immediately see that they're quite different. The big one looks a lot bigger, a lot more complicated than the little one. Let's talk about some of the differences. So the little processor is simpler. It has fewer functional units. If we look at the functional units over here, there are only 5. Integer, multi-point, multiply, load store, floating point, and the like. The big processor has a whole bunch more. If you look at this, it's got 8 functional units. And it uses these more functional units by doing complex stuff such as out-of-order execution. But not only does the big one have more units, it's also got more of each unit. So if we look at the integer unit on the little processor, you can see that that's replaced by 2 integer units on the big processor. So now the big processor can get more performance because it can do 2 integer operations at the same time. The big processor also has a longer pipeline. If you look at the pipeline here, there are 24 stages to complete work. And the reason for that is that each stage has to run faster so it can run at a faster clock speed. The little processor has a shorter pipeline because it runs at a lower clock speed. It only has 10 stages. So if you look at all this, there's a lot of different trade-offs going on here. And this is computer architecture. This is the sort of thing we're going to look at in our class. You're going to understand the trade-offs between having 24 pipeline stages and 10 pipeline stages. You're going to understand why you might want to have multiple integer units in your processor and what that does for performance. So this is the topic of this class. So now we've talked about why they should do that. And now the question is, how can they do that? So here we're going to look at the amount of logic in a processor. So in 1995, this is how much stuff was in a processor. This continued to grow. In 1996, there was a little more stuff in a processor. In 1998, even more. 99 more. By 2001, there was a lot more stuff in a processor. In fact, if you look at the processor in 2001, you can see that a whole processor from 1995 fits in the corner of the processor from 2001. So that means you can put a lot more stuff in your processor because you have a lot more space. And the reason for this is the transistors keep getting smaller. So you can put more transistors in the same space. Now if we walk forwards a little bit to 2005, here we are 10 years later, what you see is that a whole 1995 processor fits in a tiny corner of a 2005 processor. And this trend has continued today. Intel's Xeon Phi processor puts 64 Pentium processor cores on one chip. And so what this means is, if you ask how they can do this, the answer is because of scaling. We now have many, many more transistors on the same chip, and we can use them to do different things. And ARM has decided that what they want to use their processors for is for getting power efficiency. So they use some of their transistors to make small, power-efficient processors, and some of their transistors to make big, fast processors, and they think this is the right way to save power in your cell phone. So why should they do this? Why is this the right move for ARM to make at this point? Well, let's look over time at what's happened with processors. So here's data over 25 years, from 1985 to 2010. And it's data that ranges across a huge scale. So this is a logarithmic scale. And what we're going to look at is a bunch of properties of chips. So here's the number of transistors on a chip in thousands. You can see this has grown from 100,000 up to 1 billion transistors on a chip very quickly. This is why you can fit more and more things on each chip, because the transistors get smaller and you can fit more on there. If we look at relative performance, you can see that this increased dramatically until something happened over here in 2004. And performance started increasing more slowly. If we look at clock speed, this is even more dramatic. It increased very rapidly up until 2004, and then in 2004 it went flat. We stopped at about 3 gigahertz, with very few processors running faster than that. If we want to understand why that happened, we can look at the next line here. This is power. And what you see in power is that we started out in 1985 at around 1 watt per chip, and ended up in 2004 at around 300 watts per chip. And the problem here is it's too expensive to cool anything hotter than this. This is what is known as the power wall. At this point, you can't make chips that use more power because it's too expensive to keep them cool. And this is why all these other lines change. This is what forced designers to start looking at power efficiency instead of just performance. And if you look what happened as a result of this, if we look at the number of cores, you can see that in 2004, the same thing started happening. Instead of making single cores that ran faster and faster, designers started putting more cores on there. And this is the multi-core era. And this happened because we have all these extra transistors. We can't afford to use them to get just faster performance because they use too much power, so instead we use more processors. So the answer to why should they do this? It's because they can't increase power, they need to improve power efficiency, and this is a great way to use all those extra transistors we got from getting smaller and smaller transistors every year. So what are other people doing? ARM is obviously not the only player in the field. If we look at what NVIDIA and AMD and ARM as well are doing in graphics processors, they're putting lots of very small cores on a chip. Every year they put more and more of these cores in order to get better graphics performance. If you look at what CPU developers, AMD and Intel are doing, they're taking GPUs with small cores and combining them with CPUs with big cores to give you the same sort of big little effect that ARM is going after. And the reason they're doing this is it's all about power efficiency. They're trying to choose the right architecture for the right job because it's more power efficient. If I can run code that doesn't need to run fast, and if I run that code that can run slowly on a slow processor, I can save power. So all of this stuff that we just talked about, this is to give you a feeling for what computer architecture is. Talked about a bunch of different chips and a bunch of different properties and why they're making these different trade-offs. So what we're going to do in this class is understanding performance and efficiency, knowing what's going on here and trying to reason about this. Looking at design trade-offs. So why would you want to have a longer pipeline or a shorter pipeline? Why would you want to have more functional units or fewer? And how do you build the hardware? How do you actually connect these things up so they work as expected? One really important thing to consider in this is how do you make them programmable? You're going to get a lot of experience with that in this class by looking at the MIPS instruction set architecture, but this is a real problem today. One of the reasons that GPUs haven't been so popular for compute is because they're a lot harder to program, and keeping this in mind is important for understanding what is successful and unsuccessful computer architecture. So we've looked at all this, and now the question is, why should you care about this? And the answers are pretty straightforward. Computers are evolving very fast. You need to understand how they work in order to be able to understand how they're changing. And this understanding is critical for performance and efficiency. When you write code, you need to know how this affects your code. So it's not just about designing hardware. If we look at the examples I gave you, how does the big little design from ARM affect your software? If you're going to be writing software for cell phones in a few years, you're going to have these big little processors. How do you optimize your code for it? The same thing with a CPU and a GPU. How do you optimize your code for that? So in addition to these reasons, computer architecture is fun. It's a great combination of experimentation and engineering that comes together in a field that people really care a lot about, and so a lot of exciting things happen.